Hey guys, I'm Alex, and this is my STEM Pathways Forest Fire Prediction project. This has been a long-lasting and really complicated project for me, which started when I was in ninth grade, just learning how to program. I made some really bad models that were good for nothing, but it got me interested, and I've progressed to the point where I'm working on machine learning, and this is my journey for that specific process. There are three main steps, which are data collection, model training, and model evaluation. This brings me to the first part of my project, which was data collection. These are just a few of the functions I used to download almost 80,000 separate forest fires over the course of more than 100 hours of data downloading. This took so long. Not only the development of all these functions, but working with different libraries and even learning how to just use the basic software. And when I mean it took a long time, here's a screenshot of one of the tests that we did, which took almost 60 hours. Now I'd like to move on and talk about the model training. Once I had all my data, I was able to start choosing what kind of model architecture I would like. I chose a fully convolutional neural network because it can take images of any size and shape. Then what I did was I defined two encoding layers, and these encoding layers abstract the data and apply filters to it, which learn the patterns. And in between each of these encoders is a pooling layer. The pooling layer essentially takes all these filters and aggregates their effects so that it can move on to the next filter layer. After these encoding layers, we have decoding layers. These take the abstracted data, which has been reduced in dimensions, and increase it in dimensions again. And what you're seeing is a class on the left that is my fully convolutional network. This is actually a revised version that I haven't been able to train fully, but it has the same main structure as what I was originally training my model on. And on the right, you can see a class, which is my dataset class. And this is how I implemented the data loader using PyTorch. So what you can see here are some of the very first results from my model. And this was trained on my MacBook Air, which was overheating for about 5 hours to get these results. And on the left is the loss function, which shows how far off the actual results were from the expected results. And on the right, we see my very first model prediction. And on the top is the actual data. So the top row is the actual data that was from a real forest fire. The middle is my model prediction. On the left is the model prediction raw, and on the right is the filtered model prediction. And then on the bottom is an overlay of the two. And what you'll notice is that the model prediction is actually very good at recognizing where the forest fire is and where it'll spread, and it looks somewhat intuitive. And this will be kind of talked about in the evaluation. This is a second model that I trained and a third model that I trained on the right, and these are all using the same model architecture, but they've been running for different amounts of epochs, which is passes over the entire data set. And on the left, I think we have 5 or 6 epochs, so 5 or 6 passes over the training data. And then on the right, this is 68. And I actually had to get someone with a GPU to run my code for me because this would have taken so long. But what's interesting is the difference in smoothness between the two. And the one that's been run for less time has a much smoother probability gradient than the one on the right. And what this is important to note is that the more times it's been trained on the same data set, the more chaotic and the less crisp the prediction is becoming. And what this signifies to me is that there's something inherently wrong with the training data, and this will also be talked about more in the evaluation when I kind of talk about the accuracy and precision. Now I'd like to move on to the evaluation. This is a video of me starting the evaluation script, which checks almost 10,000 forest fire instances that the model has never seen before and evaluates them and compares the result to the actual data. And I actually got a very high accuracy of almost 97%. And while this might sound very good, it's actually due to the way that accuracy is being measured. This not only includes forest fire predictions, but also predictions where the fire isn't. So if you imagine the images that you've seen before, all the spaces where there's no fire count towards the accuracy of the network. And this is kind of, while this is technically the accuracy of the model, it's not very precise and it's not very useful for actual forest fire prediction, although it does have a very high accuracy. What I'd like to bring up is that the data itself likely has many flaws in it. And this example really highlights that. The left is the fire before, and the right is the fire after. And what's so striking is the very clear fire line and very clear burned area before, and then a very kind of sporadic and unintuitive, unexpected after picture. And what this kind of tells you is that not only are firefighters influencing it, but there are many factors that the data just can't encapsulate. And for that reason, the model is trying to learn something very chaotic, and the model isn't learning on very clean, natural data. And likely there are firemen that are putting out certain parts, and this is not accounted for in the data. And so the model is learning a forest fire that is essentially not natural, and for this reason, it's not a very good prediction. Thanks so much for watching my STEM Pathways Forest Fire project. So far, this has been a very big learning experience, and it's been really fun, and I'm really looking forward to continuing the project, not only for my own sake, but to see where I could push this. And that would include getting more data, including more complicated architecture types, and really seeing how far I can push the training. Thank you.